Why, hello there. Today we are doing this kind of stuff. We are integrating with long division and some other antiderivatives of trigs. Okay, so we're kind of building upon what we did yesterday with our inverse trig integration and regular trig. So this says that we're going to have to do some long division because there's no formula for this type of an integration. Okay, so if you remember from years and years and years ago, when we do long division, we want to see what do we have to multiply x squared plus 4 by, the divisor, in order to get 3x cubed plus 2x plus 5. And that goes underneath. So 3x cubed plus 2x plus 5. Okay, it's important to remember, though, that we're missing a power, right? We're missing an x squared in here. So let's add our 0x squared because we don't have that term present. Okay, so we're going to perform some long division, some polynomial long division. So the thought process is, what do I have to multiply x squared by in order to get 3x cubed? And hopefully you know that's a 3x. Okay, so I put the 3x above the x column. Right here we have our x cubed column. Here we have our x squared columns, our x column, and our number column. Okay, to keep our problem straight. So now we do the multiplication. We do 3x times x squared, which is 3x cubed. And we do 3x times 4 also, giving us a plus 12x. Okay, so this is polynomial long division. Now I'm going to subtract to cancel these things out. And 2x minus 12x is negative 10x. And we, of course, would drop down our plus 5. Okay, so now we turn and say, is there a number that I can multiply x squared by to get negative 10x? Okay, and that's a no, which means that our polynomial long division turns out to be 3x plus negative 10x plus 5 over x squared plus 4. Okay, so that's how we're going to rewrite our rational thing over here whenever we have a power larger on the top, right? This is a top-heavy rational function. So whenever we have a top-heavy rational function in calculus, we have to do some polynomial long division in order to write it as something that hopefully we can use u-substitution for. Right? That's what we've been studying for a couple of days. So we want to see if we can use some u-substitution to take the integral of this thing. So let's rewrite our integral. We're actually going to find the integral of 3x plus negative 10x plus 5 over x squared plus 4 dx. So we're going to use one of our properties of integrals, and we're taking the integral of a sum, so we can break this into the sum of our integrals. So we have the 3x dx plus the integral of minus 10x plus 5 over x squared plus 4 dx. Okay, and in fact, this sort of looks like something that might be familiar. Okay, when it comes to our arc-tan, right, your arc-tan integral comes from something that has dx over u squared plus a squared. Right, so we kind of have that on the bottom here, right? We have a number squared, which is 4, plus, or the u squared is the x squared part, and the a squared is the 4 part. Okay, so we kind of have something that looks like an arctan integral. But then we have all this junk up here on top, right? We don't want any junk on top. We want to have a 1, right? A 1 dx, or maybe a 4 dx or something. So we're going to, once again, split this into 2 fractions. Okay, so the trick here is to split into 2 fractions. Okay? We're going to split it into two fractions because we want to make it into an arctan situation, right? The integral of something that gives you arctan as your answer. But in order for that to happen, we can't have anything powerful in your numerator, right? So we're going to break this into two separate fractions. So we still have our integral of 3x dx, right? That guy's still here. Plus, we're going to split the negative 10x, so minus 10x over x squared plus 4 dx, plus the 5 over x squared plus 4 dx. Okay, so we can rewrite this fraction as negative 10x over x squared plus 4 plus 5 over x squared plus 4. Okay, which is why I am integrating each of these things separately. So now I have three integrals that I'm going to take. Okay, and each of them are fairly simple. So 3x dx, that should be an easy one for you to integrate, I hope, using the polynomial rule. So what's the integral of 3x dx? 3x squared divided by 2. Okay, so that comes over here. 3x to the second power divided by 2. Okay, now let's go back and look at this one. What type of integration method should we use here? Okay, if we pull the negative 10 out front, minus 10 times the integral of x over x squared plus 4, right? Maybe this is a good job for u-substitution. Because notice the numerator is almost the perfect derivative of the denominator. Okay, we have an x on top and we have an x squared on bottom. So this is a pretty nice u-substitution integral. So let's come over here and I will rewrite it so we can work on it over here. So negative 10 times the integral of x over x squared plus 4 dx. Okay, so using u-substitution, I'm going to call this u. So u is x squared plus 4, which means du is 2x times dx. And when we solve this for dx, we get du over 2x. So now I'm going to replace my dx and my u value. So let's see, what do I get? Negative 10 times the integral of x over. This is now u, and this is du over 2x. Okay, and this is why it's a good candidate for u-substitution. Your x value here divides your x value there. Okay, so we're also going to pull the 2, right, the 1/2. We're going to pull this to the front also. And we have something that looks like negative 5 times the integral of 1 over u du. Okay, and from our discussion yesterday, what is the integral of 1 over u du? Natural log of u. And what was our u value from up there? X squared plus 4. Okay, so this is the integral of that middle thing. Negative 5 natural log of x squared plus 4. Okay, minus 5 natural logs of x squared plus 4. Now we have to deal with our last integral.
Oh, this is all for A, right?
This is all for one problem, which is why there aren't many of them on the AP test. Right? It's a multiple choice part, so they're going to give you all the answer options, and you have to match up which one works the best. Okay, so work through as much as you need to work through in order to figure out which answer they give you. I mean, they give you all the answers. You just have to find the one on the page that matches up with what you know how to do. Or, heaven forbid, guess. Okay, so let's take the integral of this one. Right? This, if we move the 5 out front, is an excellent candidate for our arc tan. Okay, so this right here is exactly what our arctan setup looks like. 1 over u squared plus a squared. Okay, so this automatically becomes, okay, let me write that down right here, pause. So that is the integral that we're looking for, right? 1 over u squared plus a squared equals 1 over a. So we have to do a little bit of solving here, right? This should be a, so a squared equals 4, which means a is 2. So everywhere we see an a, we're going to put a 2 for our problem. And then x squared, so we want x to be the u value, right? So if u equals x squared, then so we're going to have an x up there. Okay, so this is the last part of our problem. Plus, right, we have a 5 out front, so that's going to have a 5 on top. Plus 5 over 2 arctan of x over 2. And then, of course, because this is an indefinite integral, plus c. Okay? Yes, there was a lot to this one. Right? There was the normal integral that we've done before, a polynomial style. And then we had the natural log one that we learned about yesterday. And then we also learned about the arctan integrals yesterday, plus c. Okay? And this all came because we used some polynomial long division to change our top-heavy rational function into a polynomial plus a bottom-heavy rational function. Okay, so what else do we have here? We have this function. Okay, no, we're not going to call this u. We're going to try and change this into another trig antiderivative. Okay, and we're going to do that by making it into a parenthesis thing squared, right? That's what we want. We want u squared plus a squared. And the only way that we can change things into parentheses squared is by doing this algebra called completing the square. Okay, so how we do that is we try and make this into a perfect trinomial by adding something. And if we add something to our mathematical equation, we also have to subtract something in order to stay balanced. Okay? So this is going to be your perfect trinomial, and then the rest of it is going to be your a value. Okay? So what number makes this into a perfect square? To do that, we take half of this value, so negative 4 divided by 2, and then we square it. So 4. 4 goes in this box. 4 is what makes this into a perfectly factorable trinomial. But we also have to add our 4 out here in order to stay balanced. Okay? So this is adding 0. Right? I added 4 here, which means I have to subtract 4 there so that I actually add 0. So this now is a perfectly factored trinomial. F factors to x minus 2 quantity squared. Because that's the number that multiplies to give you 4 and adds to give negative 4. Negative 2 and negative 2. So it's 1 factor squared. And then 7 minus 4 is plus 3. Okay, so this is our new denominator. Right? This is the new denominator, so we have dx over x minus 2 squared plus 3. So believe it or not, this is your u value here, and this is your a squared. So it might not look exactly like you want it to, but it has all the parts for an arc-trig anti-differentiation. Okay, in fact, this is once again an arctan antiderivative. Okay, so remember that was 1 over a arctan of u over a. That is the antiderivative of something that is dx over u squared plus a squared. So let's come over here and figure out exactly what we have to write. So if we had x plus minus 2 squared, that means u is x minus 2. right? It was plus 3, so that means a squared equals 3. So a is root 3. So because this is an arctan, it's 1 over root 3, right? That's the a part that we had talked about up here, times the arctan of the u, which is x minus 2, over root 3, the a value. And then, of course, because it's an indefinite integral, plus c. Okay, so sometimes we want to try and manipulate our denominator so that it looks like something we know the antiderivative of. Right, not the u-substitution, but in this case, an arc-trig or an inverse trig, whatever it's called, integration.
One of each.
So let's take a look and see if we can decide what method to use. Right? Are we using u-substitution? Are we using a direct antiderivative? Or can we potentially use an inverse trig integration? Okay, you need to know when to do what, or long division potentially. Okay, so looking at our first example, we have 4 over x squared plus 9. Okay, so you should know the first thing that you want to do is pull your numerator out to the front of your integral. Okay, anytime you see a number on top, the properties of integrals say we can pull it out to the front. So we now have 4 over 1, or 4 times the integral of 1 over x squared plus 9. Okay, so what method would you prefer to use in order to take the antiderivative of this? This would be an an inverse trig integral. Okay, this is an inverse trig integration. Okay, so you need to recognize this is your u squared, this is your a squared under 1. Whenever we have a 1 on top, 96% of the time, you're going to be doing an inverse trig integration. 96% of the time. So this is 4 times, right? This is an arctan antiderivative. So 1 over 3, because if our a squared is 9, then your a value is 3, times x over 3 plus c. Okay, which would of course be 4/3 arctan of x over 3 plus c. Okay, so whenever we have a 1 over things that are squared, 1 over things that are squared, you're going to be using an inverse trig integration. So our next one, right? First we're going to once again pull the 4 out to the front. So 4 times the integral of x over x squared plus 9. Okay, so what method would you use for this antiderivative? This is going to be a u-substitution method. Okay? And this is why you know it's going to be u-substitution. So in our numerator we have x, and in your denominator we have x squared. So the numerator is the derivative of the denominator. If the numerator is the derivative of the denominator, then u-substitution is the best and easiest way to go. So you need to be able to recognize when to use u-sub and when to use something else. So if we're going to use u-substitution here, your u is going to be x squared plus 9, which makes your du 2x times dx. And dx is equal to du over 2x.
Wait, so how is the top derivative and the bottom?
X over u, so we have u in the bottom, and then our dx is du over 2x. Okay, and this is why it's the best method, because your x in the numerator cancels out with your x in the denominator. Okay, so we can pull our denominator of 2 out front also, making it 4 divided by 2, or 1/2, 4 times 1/2. So 2 times the integral of 1 over u du. Hopefully you have memorized 1 over u as knowing that's the natural log antiderivative. So 1 over u has the natural log antiderivative. And now I'm going to replace u with x squared plus 9. Okay, so if your numerator is basically the derivative of your denominator, then u-substitution is the best way to go in order to find the antiderivative or the integral of your function. Okay, and then exactly what we talked about earlier today, if we have numerator and denominator that have the same power, or the denominator is greater, you're going to use long division and break this into a lot of different integrals. You're going to have the sum of a bunch of integrals, some of which might mean u-substitution, some of which might be inverse trig integrations, like we did in example number 1. So if your top power is the same or greater than your bottom power, you're going to use polynomial long division in order to find the integral. So if you were going to do part C, the long division, this would be the answer that you get all the way down here. So right, we bring the 4 out, we long divide over here, and we get this. We split it into 2, and then we take the antiderivative all the way down. Okay, so hopefully this helps, and you have a better understanding of how we do all the crazy stuff in AP Calculus. Okay, bye.